Thank you, Matt.
In the interest of staying on schedule, we're going to go ahead and start. We have 3 more talks this afternoon. I want to thank Jonathan Claudius for coming after apparently there was a miscommunication at HackerCon this year, and Jonathan was supposed to speak, and when he didn't show up, we were kind of concerned that maybe something bad had happened. What had happened is I had neglected to send him an email to confirm that he was speaking. So, as a to make up for it, I asked him to come speak at AIDE. So, Jonathan Claudius.
Thanks. So, as Bill has mentioned, my name is Jonathan Claudius. I work at TrustWave, and I work in their Spider Labs research division. So the stuff that I do every day is focusing specifically on vulnerabilities that are known, and then also discovering new vulnerabilities that we can go and reach out to software developers, help them determine where the issue is so that they can fix it themselves, and so we can do an appropriate disclosure after the organization has provided a patch to the solution. So that's what I do. What we're talking about today is this term that I created called BNAT, and I guess we can just get into it. But before we do that, I have a quick story. Before I joined the research division at TrustWave, I used to work in the MSS division. MSS division is focused on managed security services. So we would manage firewalls, we'd manage IDS appliances, and a variety of other security products that were geared towards protecting the network or protecting data on the customer network. Well, I came there from a pen testing background. So for a number of years, I flew around the country breaking into banks and organizations to help show them where their weaknesses were so that they could address those weaknesses before the bad guys do. So when I came to the MSS division, it was a big surprise, mainly because when I found a problem, it wasn't that I had to do the reporting aspects of it, which we talked about before, but I had to actually figure out how I was going to solve the problem for our customer. So my background is typically in networking, so I was drawn towards really the networking problems that existed within our customer networks. Those were with existing customers that had really complex networks, and new customers that had complex networks but didn't have any security applied to those networks. So in a lot of cases, we would introduce a firewall or we'd introduce a device that started enforcing controls, and we'd start breaking things right away. So one of my specialties was going in there, working with customers, figuring out how could we solve these problems. And when you start to get to the guts of it, and that's really where my eyes really opened, in the sense that I needed to look at some of these issues, and I found that in some cases, like, traffic would be doing like loop-de-loops to their network. It wasn't just a straight path that you normally expect when you look at a packet capture, where you can see, request comes in, request comes out. It's same on both ends, just all the bits are flipped, right? So I was out at the bar one night, and I was kind of venting to my friends who are currently pen testers. I was like, dude, this is a lot harder than what we used to do. We used to break networks, we used to write down all the details, and we ship it off to the network administrator, and we'd say, fix it. So I was kind of explaining how I went through some of these issues, and in one case, we actually got to a point where I had to whip out a bar napkin and a pen and start writing these things down, like showing them, like, traffic goes through this loop, it goes through this loop, it goes through this loop, and then it comes out the other side, and the customer wants me to just make it okay. They want me to fix it up on the firewall instead of fixing the issue, the real issue that they had. So as the beer started flowing, I'm getting more and more bold and saying, oh yeah, you know what, if I was on the pen test side, I could totally hack this. I could totally break this stuff and turn it into something that an attacker can use. And typically a lot of the issues that we dealt with is traffic was working before, or they got it to work, but because of what they've done, traffic is broken and there's no communication that can occur. So what I suggested is that I can take these issues, I can take these problems, and I can turn them into opportunities for myself as an attacker. So I can take this stuff, I can do some magic on the packets, and I can turn it into something that myself and those that are skilled in the art of pen testing can use to start attacking a network and gain access to things they're not supposed to be able to get access to, that most of the industry assumes is not accessible. So that's what got me on this path. It's kind of, after that night I got thinking, I was like, all right, let's try this, let's try it. And what I found out was that it was a lot harder than I originally expected. It took me a lot more time than I thought it was going to take to sit down and start causing some anarchy for these types of situations. So what we'll be talking about today is the process that I went through to slowly step through the individual pieces of how you can actually go about causing anarchy or problems with these types of situations. So I'm sure you're all wondering at this point, what the heck is BNAT? What are you talking about? What is this thing? BNAT stands for Broken Network Address Translation. And what happens is that with NAT, you have it's called Network Address Translation. Basically what it means is traffic, as it traverses like public to private networks, there's modifications that need to be made on the packet so that they can be understood by both the client and the server in both directions. In some cases, if things take different paths that they're not supposed to take, or if they don't take the paths that they're supposed to take, we can end up in situations where modifications can only happen on half the stream. So we can have, there's a situation where I can have traffic from client to server be unmodified and traffic from server to client be modified, or vice versa. And that can cause communication to break down. The first example I have of this is when a client is communicating, he's on the internet, he's communicating to another server somewhere out in the internet. He sends traffic to this 2.1 host. It goes out to the cloud, does all its magical routing stuff. It gets understood by the server, and it comes back. But what we find is that, excuse me, the traffic that's coming back is coming back from the wrong IP address from which we requested. This is the basis for what we're going to be talking about today, so I hope everyone's listening. But what happens in this scenario is that when I get a response packet that comes back from an IP that I didn't request, my TCP/IP stack looks at that and says, that's not from which I requested, and it just shuts it down. It just takes the request and it sends a reset packet, and if we're talking about TCP traffic specifically. So I've got two examples. What you get is you get a SYN. You guys familiar with the TCP three-way handshake? Someone help me out? Right. So I have these first two packets that look good, but what happens is that when this guy sees that second packet come back, he's like, no, that's not mine. That's not something I requested. So what he does is he shuts it down and he sends a reset packet, and the communication both on the client side and on the server side is shut down. So you can't communicate anymore. Like game end over, like can't do anything with that. So that's one example. This is what an attacker sees. But what I want to show you here in a second is how the heck does this actually happen? Like, why does this happen? So maybe we can get a better understanding of it. So the first example I call BNAT on a stick. BNAT on a stick is when you have a client that's sending a SYN request or initial communication request in through a firewall. What happens is on the firewall is that there's a NAT operation that needs to be applied to that traffic. The first operation, at least in typical scenarios, and I'm sure there's tons of different types of NAT, is that we have a simple DNAT. A DNAT means that we're performing a modification of the destination IP address of the traffic on its way in. So what we have here is, say this client's out here on the internet, this firewall, its public interface on the internet, its inside interface on the inside network, and this guy's in a private DMZ somewhere. So what ends up happening is we make the modification, it gets sent to the server says, okay, SYN request, yep, I have that service open, everything's good. He goes to respond with the SYN-ACK, but when he responds, the firewall consults its NAT table. NAT table is just like an access list or any type of list that we use in networking, like a routing table. It's processed in order. So if there's a NAT rule that's wide enough that sits before that dynamic allocation that was created when this guy came in, what can happen is that traffic can catch the wrong NAT rule and the wrong IP can be placed on the source IP address of this traffic after it comes outside on the public network. So what ends up happening is the same situation that we talked about in the beginning. We end up in this weird situation where we send a request to one IP and the wrong IP responds and it shuts it down. Reset, connection over. So that's one example. The next example is actually probably more likely. I think for a lot of people it's a lot easier to rationalize, is a situation where you can have a BNAT loop. A BNAT loop, is anyone familiar with asymmetric routing? Raise your hand. All right, great. So asymmetric routing is just like we talked about, or at least I think I alluded to it a slide or two ago, is when a communication channel, when you have traffic that traverses from client to server via one path, and then from server to client the other path. So you end up, it's kind of like Google Maps, if you think about it that way. You know how you say, like, I want to go from here back to the airport, and I go and I say, give me the options. It gives me multiple routes. So in networking, we can have the same thing, where, for whatever reason, this being one example, that we can take one route to get one place and a different route to get back. So in this case, what we end up with is a SYN that traverses this firewall. We start the connection up. SYNAC comes back, it goes to the router, and then the router source nets that traffic to its public IP address. Because it doesn't know anything about this original connection, because it has nothing to do with it. This is an entirely different part of the network. You can even think about this as one country and another country if you're a global organization. So these are just two examples of many that I found that allow this stuff to occur. And it doesn't just happen on IP addresses, it can happen on any aspect of a packet, enough to where you can actually cause a communication channel to break down. And in a lot of cases, with TCP/IP, it's really restrictive. So it requires very specific things that, in order for this communication to actually be able to stand up. So the question I asked myself was, how can I take this broken crap, how can I take something that someone screwed up, and how can I fix it so that I can attack it? And the first step of that was actually completing a TCP three-way handshake. How can I complete a TCP three-way handshake in this particular scenario? How would I do that? So it took me a while. I thought about it for quite some time. In fact, one of the conferences I was at DEF CON, and I was explaining it to a friend of mine. He's like, "No, you should just do it." I'm like, "All right, well, I'll do it." I came up with this idea. There's a couple steps that potentially you could take to cause this handshake to actually complete. So those are actually right here. So what we can do is that, remember how I mentioned in the first case, is that there's this reset problem. If the reset gets sent from me to the client, all bets are off, like connection over. So the first thing I needed to do is I needed to stop the reset packet so that the reset packet didn't close down the connection, and we can keep things moving just a little bit longer so we can cause some additional stuff to occur. So we stop a reset. We need to accept that SYNAC and actually be able to understand it. Because previously our stack doesn't have any knowledge of that packet being associated with any connection. So we need to manually catch the SYNAC, we need to look at all its attributes, and then we need to forge an acknowledgement packet that matches what the server is expecting. Does that make sense? So we do some magical stuff, just a couple, three things. So I used a couple tools in the process of kind of mocking this up. I had to provide a POC or no one was going to listen to me anymore. But the first step was using Ruby packet foo. It's a gem that you can add on to Ruby so that you can start interacting with packets at a programmatic level without getting too deep in the weeds. I was actually not a programmer. I mean, I'd done some scripting. In fact, this is the first thing I ever did in Ruby. But the packet foo project was created by Todd Beardsley. He's typically associated with the Metasploit project. The gem itself is heavily used in the Metasploit project for flinging packets and exploits and stuff like that. But it turned out really useful for me. It also used Linux IP tables, which I'm sure some of you are familiar with. It's a kernel-based firewall that's available on most Linux distributions. So within a couple of commands, you can do some pretty powerful stuff. So the first step that I mentioned, I need to stop a reset. I need to stop a reset from my client, not from anywhere else. So I can actually put this line that I've put up top here, this IP tables command, into a command prompt, and I can actually selectively stop resets from coming from my system. So I'm not going to send any more resets. So example of this is this next picture right here. I've got the initial request that comes in, SYN, SYNAC, no reset. So that means I still have the connection wide open, and we can still do stuff. So the next step was accepting the SYNAC. I'm not going to go through this code here. I'm just going to tell you what it does. The first step, setting up a packet capture. If you guys saw John's talk earlier today, he talked about BPF filters. So what I did is I start up a packet capture. I use just a really light BPF filter, and I say only look for syntax. Only look for syntax that match the information that I'm looking for. So I find these syntax, and then I have a loop that just processes them. All right, got it. So what we do here is at this point, this packet variable, it's an object that represents the packet that we received. So it's got all these like knobs and methods and attributes to it that we can set or we can read. So once I've received the SYNAC, I can then go and I can forge an acknowledgement using the attributes that I got from the original SYNAC. So if you think about TCP/IP communication like an envelope, like I'm going to send you snail mail, in the upper left-hand corner I have to put my address and my information, and then in the other part I have to put the person I'm sending it to, their information. So what happens is as we send letters back and forth, we just have to swap that information. So when you think about it at the TCP/IP level, there's a bunch of attributes that we need to kind of cross our wires so that we can talk back and forth to each other. What we're doing here is instead of sending the reset, we're just doing what we normally do during TCP/IP communication, but my stack doesn't have to be involved in all the magical stuff. I can just do it right here. So what ends up happening is I can send this reset back down the path. So I have a diagram to explain this. Like we talked about before, we've got a server, we've got a client, we've got two systems that we're communicating through. This is the second example. So this is being on a loop. So we've got traffic that goes through a loop through this network if someone tries to make an initial request. So the first step, like I said, we send a SYN. The SYN request comes in, it's DNATed, it gets to the server. The server then consults its routing table and says, who do I send this to? And his default gateway says, or his routing table says, you got to send this to router. Now that can happen on the device, or it can happen through any interim device that this device has to talk back to get back out. So what happens is we end up with a SYNAC that comes back. That SYNAC is modified with the wrong IP address, like we talked about in the couple examples before. But this is that stage when all that code that we were looking at before actually takes place. It actually starts to have some action. So we suppress the reset, we read the SYNAC, we modify some variables, and then we forge an acknowledgement packet back on the wire. So what ends up happening is all these hosts are happy, and we've completed a TCP three-way handshake with something that, for all intents and purposes, the rest of the world would never consider that this is an open port. Any questions right quick? Or are you following me? All right. When I first started explaining this concept, even to like my close friends that are in security, they're like, come on, dude, that's not going to work. That doesn't make any sense. So I'm glad that you're all following me.
So the one question I do have is that you found that some of your clients actually viewed that on the server side that port was closed to the client side?
Yep.
Because of just a bad routing?
Yeah. Because they're not implementing bad routing as a protection mechanism. They just have bad routing, so they don't know that this host is exposed.
Okay, because I just find it so hard to believe that they actually believe this, that they're secured.
So customers aren't looking at this like, I know that this exists and I'm secure, so ha ha ha, hackers. No. It's different. It's, I have this configuration, I don't know what it does, but when I go through pen tests and I go through port scans and I do all the security stuff that I normally do, I come up clean. Okay. And actually that makes a really good segue into the next section is, how the hell do you find this stuff?
Yeah.
One of the things that I said, okay, I can do this in a vacuum, but like, how do I go out there and how do I find examples of this when it happens in the wild? How do I go sweep the internet and find all the bad BNAT instances out there? Well, the first thing I went for was Nmap. I mean, if you guys haven't heard of Nmap, it's like the de facto standard for who uses Nmap. There you go. So, what was that?
They use it in APTs.
Oh, the APTs and yeah. So I went to Nmap and I said, okay, I'm going to use Nmap and I'm going to go figure out a way to scale all this stuff. But one of the problems was I initially just ran right into a brick wall. And what's interesting here, and you might not be able to see it all, John, I'm loving that you gave a BPF explanation earlier. This is a BPF filter. This is Nmap run in debug mode, or in pseudo mode. What it does, it actually tells you the Berkeley packet filter that it's using to determine how it receives responses. So when you look at this, and because at first I scanned this stuff and I was like, man, I'm getting filtered ports, I'm getting closed ports. What the hell's going on? Well, if you look here, it specifically outlines what IP address I'm expecting responses to come back for. So Nmap expects things to be symmetric in that I have to, the syntax that I receive have to come back from the same IP address. It's like, I'm not faulting Nmap for this because the rest of the world thinks of TCP/IP this way. That's how I understood it. But when you go and you run a port scan, like I'm port scanning a system here, this 2.1 host, I end up with port 8080, which I have a service on, but it comes up as filtered. So like, from a pen test perspective, guys, if any of you guys are pen testers, what do you do with a filtered port?
Yeah, move on. You treat it as closed.
You treat it as closed. It means it doesn't exist. It's, you know, I can't touch it. I can't do anything with it, right? I mean, that's pretty much the assumption, right? Well, that was my assumption too, until I was kind of falling down this path. I was like, well, shit, I need to figure out a way to detect this stuff. So I wrote a little BNAT Scanner. It just goes out. It'll look for request responses. So what you can see here is I requested 2.1, got a response from 2.2, and it came back on port 22. So that means that there's an SSH daemon here that I can port scan, and it comes up as filtered, but there's something there. Like, I can get responses from it, but it's just not quite right. It doesn't exactly match up to what we're expecting. So I needed to write the scanner just a little bit more open. In fact, I had to write it the inverse of Nmap. I had to look for situations where I had almost all the attributes, but not all the attributes right, in which the Nmap would have considered it as closed or filtered, but I can see it as open. There's something there that I can do something with. So that was cool. I can scan stuff. So then I went and said, okay, I'm going to scan 250,000 hosts and figure out how many are out there. So what I ended up doing is I ended up selecting 10 common ports. Some were like really common, and some were just like, oh man, it would be really cool if I could find this on the internet. Like SMB services or database servers that I shouldn't be able to see publicly accessible.
RDP.
But yeah, RDP, exactly, that was one of my ports. So I did that, and what I found was that 1 in every 800 devices that were live came back with a BNAT service. I know this sounds like mind-blowing, right? I see you, you're like, what the fuck?
Did you do the same scan within that to see what the difference was?
Well, so specifically what I did was, this does the inverse of Nmap, so it definitely wouldn't have found it. But what I ended up doing is we ended up providing publishing a report every year. I don't want to spend too much time on it, but you can get more details there. We did some like country code and like frequency stuff. It was cool. But yeah, it's out there. It's stuff that's publicly accessible on the internet. You can get to these services, but if you scan it using the normal tools that we all use, you're just not going to see it. So just something to think about. So the first step that we talked about was how to complete the handshake. Now we talked about how to find it. Then we want to talk about, at least I want to talk about, how do you actually talk to the service. So like what we talked about in the first example is all in a vacuum, right? Like, yeah, I can complete the three-way handshake, whoopity-doo, right? I can go and I can get that ACK all the way down the path. But what if I want to continue talking and I want to continue doing stuff with this service so that I can evaluate it like any other service that I would find on the internet and make it basically the same? So what I did was I had a little bit of a mission. I wanted to figure out how to continue that session along, and I had to do some different stuff than I did in the original example. The original example was really just a POC to see if I could get it to work. But I had to try a couple tools. I tried to do IP tables because in this situation I had to do some routing. At least the strategy that I took to try and solve the problem, I had to do some routing. So I tried IP tables, but I ran into some problems. And this is pretty interesting that a lot of people, when they do port scanning, they do it from behind a firewall. Like if you're a pen tester, you'll do it from behind. Sometimes people do it behind a firewall. Sometimes people do it on their edge. But what I found is that IP tables is great for is a great stateful inspector. It'll basically stop any like non-state traffic that's coming back. So what you'll end up with is IP tables will just block all the traffic at your gateway and you won't be able to get anything through. But I wanted to use IP tables because it's highly configurable and useful. So I wanted state tracking, but I really didn't. So I had to kind of be in this little middle space. I tried a tool called IP Route or IP Route 2. I think they deprecated it as of like 2.4 kernel. It was cool because it said it would do like non-stateful natting. I wanted to be able to pass traffic through and just modify the packet hardcore. Didn't want to deal with any state tracking because for all intents and purposes, people would consider this non-stateful. And I also looked at trying to do like a Ruby implementation all by myself. But what I found is that each one of these pieces of tools, with the exception of IP Route was a real pain in the ass and it was like really cryptic. But what I did is I took all these things and I tried to pull out the best parts of them and throw everything else away. So this says exploit, but this is more supposed to mean talk to the service. So I used packet foo again to write kind of a custom NAT implementation that allows me to deal with this sort of situation. So I could make the modification to the packets on the wire. I can use IP tables for the selective suppression and get it to stop the resets that I needed to stop. And then I can also pair that with a vanilla client. So like any one of your machines here would have worked perfect for that purpose. So the purpose here, the reason why I used a vanilla client, and the reason why I took this approach is that if you've ever done any like low-level networking stuff, the first thing that you got to think about once you get the TCP networking up is how am I going to handle all these protocols? And I didn't want to be writing like application layer gateway stuff. Like I didn't want to be like writing protocol stacks for everything under the sun. I just wanted to be able to use this connectivity and let my client figure out whatever protocols or things it wants to talk. So I ended up writing this thing called BNAT Router. So BNAT Router sits in front of a vanilla client so that the client can talk through the BNAT Router and communicate with the destination service completely unknowingly that there's this like weird situation going on. So we just kind of fix things up in the middle, and then on both sides of the connection, both the client and the server, they just think they're talking to a normal service. But there's definitely some foul play going on in the middle. So we're kind of man in the middling to get unbroken. Probably a bad way of saying it. But here's an example. So we talked about the original example where we've got the router talking to the firewall through the server. But we have this additional host here. This is our vanilla client. This is the laptop that you have in front of you. So we send the SYN request. The SYN request goes through, gets DNAT'd in. We get the SYN ACK, comes back through, and then we get an ACK that comes back through. So it's kind of like a proxy if you think about it that way. But it does in fact do routing. So what you end up with is a happy connection all the way through. And all this guy is doing is just a loose version of my version of NAT. So he just handles like the fix up and all the stuff that I don't want to deal with. So what does that bring us to? So this is kind of this is the fun part for me. So I had to figure out, okay, I got TCP networking working. I can actually talk to the service now, and I can talk to it just like any other service that you would talk to on the internet. Just any web server, it's all the same now. So now I had this kind of quandary is that this stuff's kind of a pain in the ass to set up. It's kind of annoying, I'll be honest. But one of the things I wanted to do is I had some goals again, and I wanted to make sure that it was portable. I want to make sure that it was easy to use for people, and I want to make sure that it was available to everyone. There's a lot of people out there using the Metasploit framework, so it seemed like a logical step to take to port some of my code into Metasploit so that people could start using it to attack these sort of situations. And again, I wasn't super, I was already writing in Ruby, so Metasploit's written in Ruby. It seemed like a perfect marriage. So I was at DEF CON, and I met this guy that I hadn't seen in 10 years. We actually used to ride the elementary school bus together, in Western New York. There's probably 20 people in our town. But I ended up running into a DEF CON, and he's like, hey, I work at Metasploit. I'm like, oh, cool, I'm like, I have a talk later if you want to go see it. And I ended up giving this presentation at DEF CON, and he saw it, and he's like, dude, that's cool. We should have that in the framework. I'm like, cool. Well, guess what? I wanted to put it in there anyways. I just didn't know how to do it. So David actually helped me take the code that I wrote, port it into Metasploit, so that people can start using it. So if you have Metasploit or using Metasploit, if you update at any sort of frequency, you probably already have it on your system and you don't know. He goes by MSF Bandetta on Twitter, so he's a pretty cool guy. He's doing like low-level exploit stuff. That's pretty much all he does. So I wanted to do a demo today to set up a little bit of a scenario to talk about how would I do this and kind of put all these pieces, these kind of disparaging pieces together into something that I think a lot of us can connect with. So I wanted to set a scenario where we're doing an external penetration test on an organization, and we have a BNAT services there. We don't know it's there, but it's there. If you scan it with normal Nmap or normal tools, you wouldn't see it. But what we're going to do today is we'll actually show how you can actually exploit that service remotely using these tools. So just bear with me while I pull that up. All right. Lose this. It's going to do some stupid VMware stuff. Stand by. All right. So, this might be hard to see. I'm not sure. Do you think we could turn the lights off for a minute? I think it would help. Unless anyone's worried about cooties.
Mood lighting.
All right. I think it'll be easier to see the white on black. Is that easier to see now?
Yes.
Cool. So, while he's doing the rest of that, so the setup for this is I've got this service. There's a BNAT service on port 8080. I don't know it's there, but I kind of do, right? This is my demo. So I'm going to do an Nmap scan of this system, and we're going to see what comes back. So again, this is what we're talking about. I did a port scan of 8080. Port comes up as filtered, right? Can everyone see that over there? Is it light dark enough? Cool. So I'm going to show you the Metasploit version of this. I think it'll maybe register easier. I also have native code that does this by itself and not Metasploit, but it seems that people are more likely to use it if they can get their hands on it. So let's move forward. So yeah, I do some highlighting and cool stuff, right? I have a more comprehensive video of this online if you guys want to see it later. So I'm going to load up Metasploit. These ended up being auxiliary modules just for everyone's knowledge. They're not like exploit modules if you think about it in the traditional sense. So you've got Metasploit up. I'm just pausing this just for a second before it runs. What we've got here is you've got to set some interface stuff, so I have to tell it what interface I want to scan on. I tell it what host I want to attack and then what ports. That can be one or many, just in this case it was just one. So I scan for it, and then the response that comes back shows that we've got a BNAT service. But if you remember in the Nmap scan, there was no open port, right? Like came up as filtered. So that's kind of cool. The next thing we're going to do is we're going to actually stand up a stateful router to handle the connection. So what we do is we set what's the IP that I'm going to be attacking, what's the IP that I know it should be responding on, so we know what to fix up, and also what's the client IP that's sitting behind this router. What we're looking at here is actually the router component, because we've identified it. Now we're going to be a router. There's going to be another host that sits behind this that communicates through it to the outside to attack the service. So it does some magical stuff. This is just me putting some debug information so I can tell that I actually got ARP responses from all the hosts that I expected to get responses from. And I start up 2 packet captures, both on the inside and the outside. And what we're going to do is we're basically just going to be listening on each side, and we're going to be picking those packets up, turning them into objects, throwing them over top, catching them, bringing them back down, and tossing them back down in the stack the way that we expect them to be gone. So pretty straightforward. So we're going to switch over to the client. And from the client's perspective, he's now behind the router, right? Everyone follow me still? So we go to netcat. We're going to forge a generic HTTP request. So we got an open port. We're going to make a GET request. And lo and behold, we have a Tomcat service responding on that service. So we communicated through, we hit the base page of that Tomcat instance, or the struts instance. Now what we're going to do is we're going to actually fire up Metasploit again on the client, and then we're going to exploit that service through that channel. So we've got this fired up. We're going to use, this is actually, I chose this exploit because my friend David actually came out with it when I was doing the original video of this. So I wanted to make sure that I used some of his work in this. So what we've got here is we're setting our host to the service that we're going to be attacking. We use the exploit specific one. We're going to attack this hello world action and the strut stuff. We're going to set the target, but we're going to set the payload to reverse TCP. And then what's interesting here is that we're going to set the L host to be the responding service. So when we throw the shell, we know where to throw it. Does that make sense? So, and I think 2.3 or .3 is the public interface of the router. So he knows to send it back to the public router and not to this client.
So real quick, the client IP address that you showed when you were doing the router,
Yep.
that's the actual IP address of the, because it looks like you're using the backtrack machine. Is that the IP address of the backtrack machine, or is that the IP address of the server?
That's the server.
I have two backtrack instances.
Okay.
One running the router code and one running the client code.
Okay,
The
so
public IP address of the router
Okay.
is the .3.
that's what the part I didn't quite get, is that you actually have two separate
Yeah.
machines running.
So from a public perspective, we have three IPs in play. We have the .1, the server that we're sending the SYN request to. We've got the .2 that we're getting the syntax back from, and then we got the .3, which is the public interface of the router. It's the attacker's
Okay.
public interface.
I thought it was just like an application proxy, so
Nope.
to speak. That
It's actually
sat
doing
there.
routing.
Okay, so it's an actual physically separate. Well,
It's not physical, it's virtual, but
but
yeah.
it's a separate machine.
Yes, separate
Okay.
box. But what I want to point out here is that I have to use this specific thing to tell the client how to do this. This is like the only kind of weird thing that I've done here, is that I have to tell it that the public interface that you send the reverse shell to is my router, not to my IP address, because Metasploit's going to put the L host of the client in there otherwise. So we hit exploit and pray. So it tries to bind to this interface, which it doesn't have, and fails. Oops. So it fails over to the 0.0.0, which is every interface. And then what we end up with is a reverse handler that's coming back. It takes a couple seconds to do. But once you essentially have a shell here, so you can run commands as if you're the user that you've attacked. So this would work for any single TCP-based exploit or service. I can't see of any situation where it wouldn't be any different, because I'm not doing anything at any higher levels. I'm just depending on the stuff that's traversing my stuff to do what it's supposed to do.
So can you run an nmap now from that client machine against that?
Yes, actually you can.
Okay,
Absolutely.
and now it'll come back with ports open. and
Exactly,
stuff
because
like
I'm fixing up the traffic, and NMAP doesn't know. It just assumes that as long as yes. Your answer is yes. Does anyone have any questions about this? I'm going to end the demo in a sec.
So in order to identify the IP that actually sends you back the syntax, I assume it's not always sequential, so it could be anything. Does your scanner just listen for a syntax that has that sequence number you're expecting from any IP?
That's actually one method that you can use. I didn't want to get into all the details today, but basically what can happen is any one of the parameters can be modified. Ports can be mismatched, IPs can be mismatched, sequence numbers can be off, but all these things can be fixed up. This is just one of the base examples that I think a lot of people can identify with, but at the lowest levels, yes. Any modification of those packets can be fixed up and sent back as long as you receive the response. You just need to know how to talk back. So yeah, that's the demo. I have maybe one or two more slides, and then we can open it up for questions. All right. So I do have some parting thoughts for y'all. I wanted to just, and I think I made my point, but I want to reiterate just quickly. I wanted to hit on the point that current tools are not identifying this stuff. So there are services that are publicly accessible, both on the internet and inside your organizations, that are reachable by attackers if they had the proper means and the proper tools. This is just one example of how you could do that, or how an attacker could or could conceivably are. It's always that assumption that if it's possible that there's a chance that someone might be using it. I personally have not seen anyone using these types of attack techniques in the wild. This is just something that I cooked up on my own time, and it just seemed to work out. As far as most tools, I think, or I would say not, most tools probably too much. There's a lot of tools out there that will handle this situation properly and will shut down the connection as it traverses out that second path. But there's also a number of tools specifically that will not deal with those situations. Cisco routers being one example. If a SYNAC traverses a Cisco router, it's not going to enforce state in a lot of cases. There's a lot of other examples out there. There's even firewall technologies that I've come across and that I've tested that will not be able to handle these situations, and will send the SYNAC out the second path. A lot of these issues are rooted in routing issues and traffic flow problems. I would say that based on my experience, most of them are routing. But from the purposes of this, I wanted to show you guys that there are opportunities out there for attackers to be doing things with stuff that we currently understand as blocked or non-reachable. I think most of this side of the room probably would have told me before we talked that if a port is filtered, there's absolutely nothing you're going to do with it. Hopefully I changed your mind a little bit, that it's possible. And hopefully maybe you take that back to your organization, have that discussion with maybe your network administrator. Hey, do we have asymmetric routing in our environment? Hey, could this stuff ever occur? The other thing is that from an auditing perspective, when I think about like having an assessor come in and evaluate my environment, this is really hard stuff to detect. This is not going to be one configuration. It's not going to be looking at the firewall config and saying, yeah, you're good. It has to consider the entire system. It's the interaction of all these devices that causes this problem to occur, and the only way you're going to find it in a lot of cases is testing it or have a very thorough understanding of your traffic flow. So that's really all I wanted to impart on you. I want to open it up for questions in case anyone has anything that they want to say or ask me. But if we don't have time or we run out of time, feel free to hit me up afterwards, and I'm glad to talk about it. We're good?
Thanks. Take a 5-minute break. Mr. Baird is next.
Yeah.
Good luck, bro.
How's it going? My name's Sean. Nice to meet you.